All right, there's a little bit of a scale going on there, so we'll talk about that in a second. 22 blocks. Because what we'll do is we'll take your common sense answers based on what you see here, and that's what you're supposed to get. You're supposed to look at it and say, all right, it's 22 blocks because I looked at the graph and it's 22 blocks. All right, but then we're going to convert into the mathematical way of denoting this sort of stuff. What is her distance from school after she's walked or has been walking for 4 minutes? What do we got there? 12 blocks. 14? After walking for 6 minutes, Erica stops to look for her subway pass. All right, so is she walking to school or not? Like, what does she need a subway pass for? I'm questioning her motivation here. Wait, is she trying to not go to school here?
No, she goes on the subway to get to school. But she has to walk to the subway station.
Erica heads out to school by foot on a fine spring day. Her distance from school in blocks is given as a function of the time in minutes she has been walking. The function is so, wait a minute. All right.
Maybe she was walking on the subway.
So she walked 12 blocks, said to herself, you know what? I should take the subway. Then walked back 2 blocks. Then said, you know what? Forget it, not taking the subway. And then walked the rest of the way?
She walked back. No, she walked back 2 blocks and then took the subway.
That's not what that says. I think Erica might be lazy. Like, she's already walked the first 10 blocks. Like, why not just go the rest of the way? She's just dilly-dallying for like 7 minutes. Erica. I'm gonna have to email home. All right, so anyway, how long did she stop for? 3 minutes. All right. How many blocks did she walk to the subway? 2. I don't like her mentality here. This is not a person who's thinking the right way. How long did it take for her to get to school once she got on the subway train? Because, you know, could be the restaurant, I suppose. 4 minutes. That little up line is the 2 minutes that it took for her to, or I'm sorry, 2 blocks that it took for her to, once she found her subway pass, she was like, all right, well now I can go to the subway, even though I passed that location like 2 blocks.
You have to take like a turn. It's a lot of blocks to walk.
Yeah, this is not, I mean, I don't know what the story is of this subway line, but I mean, maybe it's just one of those things like she's that far away from the subway. I don't know. Anyway, so let's kind of get this going in the right direction notation-wise. So the time spent. All right. Well, I'm going to call that T. I think obviously. What might not be as obvious is that I'm going to call this the vertical axis f of t. All right, because the distance is a function of time. So where you are distance-wise is dependent on how long you've been moving. All right, and specifically, we're looking at x being equal to whatever the t value is, because normally we create a graph of x against y, and y would be whatever f of t is equal to. So if I have a coordinate on a graph, now they gave us some relevant coordinates, or at least they suggested some relevant coordinates. Let me go purple here for those keeping score at home. They talked about this point. I believe it was this point. Then we had a little bit of an interval We'll get to that in a minute, but let's just focus on these 2 points. So this one would have coordinates of 0, 22. And this one have coordinates of 4, 14. All right. Each coordinate, whenever you plot a point, is going to have an x value followed by a y value. But contextually, in this situation, the x value is t, the y value is f of t. All right. So, and if you could get the notation down, it's going to make a big difference. So when they're saying, how far does Erica start off from school? Well, the starting part, that word start is a key term. All right. How much time would have elapsed, or how much time would have passed if you're just starting something? 0 seconds, right? So start would mean the same thing as 0 seconds. All right, so what they're asking us to do in this question is find f of 0. All right, f of 0. It's basically, I mean, whenever you see f of anything, it's saying what is the y value when the x value is this number. So what is the, in this case it's t and distance, but it's saying what is the distance when time is equal to 0. So 22, right? The 14 blocks. Again, in this case, it's a little bit more obvious because they're telling us flat out that 4 minutes have passed. Here they're asking us for f of 4. If I'm looking for f of 4, all I'd have to do is find 4 on my horizontal axis, go up to the vertical axis, and see what that corresponds to in terms of a y value. All right. So then in number 3, it says after walking for 6 minutes. All right, 6 minutes. I can mark that off. Let's go with that burnt orange kind of thing. I'm at this location. How long does she stop for? So then I'm looking for this interval here. Because stopping would mean that our distance is unchanged, right? So I'm not moving. So that's why we look at this, just this flat line interval, all right? So that would be a value of 9, and then all we'd be looking for is the difference between those two numbers, all right? You could do 9 minus 6 if you want, but I think it's even easier, and I think this is what you all did. You just count the box. You said, oh, I'm starting here at 1, 2, 3 seconds later, then we're on the move again. All right, so all of that stuff has a notation associated with it. So if I were to say something like, you know, at what time was she, I don't know, 6 blocks away from school, you could figure that out. You just look at the picture. 6 blocks away from the school, here's 6. It would be at this location, which would correspond to this number, all right? But how would that manifest itself in the form of a question? What it might ask is, f of t equals 6, find t. If it were to ask that, it's saying that your y value is equal to 6, find the t value that corresponds to that, in which case you would know it would be 13 minutes. All right, so being able to read the graph is really important because, I mean, I don't know about you, but I don't think it would be very easy to come up with a single equation to model what's in this picture. I mean, we've worked with inequalities and we've worked with line equations. We haven't done anything with curves yet, but even if we did, there's no curves on here anyway. Right, this is 1, 2, 3, 4 linear functions, all on the same graph. It's what's called a piecewise function, because anytime you take pieces of different graphs and smush them all together, then you're dealing with what's known as a piecewise function. Right? So I'd have to actually come up with 4 different equations to represent this graph if I wanted to do it algebraically. Whereas if I just need the information, if I just need x when I know y, or y when I know x, all I have to do is look at the picture. Right? So, you know, how long would it take me to walk 10 blocks? All right, well, I started off at 20, 22, 10 blocks would put me at 12. So I'd get to this location, find out how much time has elapsed. It would take me 5 minutes. All right, so reading it, understanding what you're reading is very important. But again, it's not always going to say stuff like, how long did it take to do this? It might say, f of something equals this, find t. You know, in which case you have to do the interpretation part on your own. All right, very important. Positive, negative regions. Positive region of a function are the intervals where the function is, well, you could say positive, but that's using a word in its own definition. Positive, right, you look at the picture, it's above the x-axis. The function is above the x-axis. All right, is where the y values are, well, it's a positive region, so, I mean, your instincts probably wouldn't tell you to say negative, so y values are going to be positive. All right. Negative regions, the function will be below the x-axis, and the y values would then be negative. All right. Picture pretty much tells you all that, but it was worth taking the time to state it explicitly. All right. So on what intervals is the function positive? Well, let me just indicate 0 here. All right. So this value, anything that's along this axis, is neither positive or negative. All right, so we don't count anything that comes on the x-axis because that's where the function would be equal to 0. All right, so I need the interval for which the function would be positive. So I'm just looking at the x values. Let me highlight the relevant part. It would be this part of the graph would be the positive part. This part of the graph, I missed, would be the negative part. Intervals, talking about interval notation. So that's the parentheses, bracket stuff, right? So my positive interval, only in terms of the x values, so these are only the x values are what I want here. My positive values start once I hit 1, right? Because anything after the 1 is fine. Right? If I choose an x value that's greater than 1, will I end up with positive y values? Yes? Excellent participation. So anything greater than 1. Blue. Any x greater than 1. How do I write that in interval notation? That's going to be inequality notation. So with the parenthesis bracket stuff. So it's starting with 1, right? Oh, is it negative 1? Sorry. Oh, it is. Thank you. I covered up the negative signs, even though I should have noticed it, but I covered it up with my black line there. So starting with -1, but I'm not including the -1 because -1 is on the x-axis, and so parentheses to exclude it. What's the highest x value? Positive infinity. And infinity always gets parentheses. All right. Now for the negative part of the function, it'd be any x less than -1. How would I write that?
Negative infinity, and then -1.
Mm-hmm. Parentheses all around. All right. The only value that's neither positive nor negative is the -1 itself, so we don't include that in either section. Okay. All right. Now, increasing, decreasing. That's talking about the slope. All right. So if a function has a positive slope, it's increasing. If it has a negative slope, it's decreasing. If it has anything other than that, then it's neither increasing nor decreasing. All right. So if it flatlines, it's a constant slope. All right. So zero slope. If it's vertical, it's not even a function. I mean, it's possible that you could have a situation contextually that calls for a vertical line segment, but not very common. I can't think of any off the top of my head. But what most people do is, because you want a visual way of thinking about it, you don't want to be thinking about it by the numbers, especially since you could be given graphs that don't have any numbers. It's all in terms of letters. You know, it might say that you have an x-intercept at A. Give me the interval for which the function is increasing or decreasing. And you're like, oh, well, how do I do that? I can't figure out the slope. I can't do a change in y over change in x. Or it's a curve. How does slope work for that? Not in a basic algebra class. It'd be in a calculus class, right? So what we do is we look at the picture. It has a positive slope if it's going uphill from left to right. It has a negative slope if it's going downhill from left to right. It's constant if it's flatline, right? So like this interval here, if it ever goes horizontal, it's constant. But basically, if you're reading a graph like you would read a book, from left to right, anything going uphill, increasing, anything going downhill, decreasing, all right? Forget about any arrows that might be on the graph, because people look at this and say, oh, it's decreasing, clearly. Just look at the arrow. It says it's going down. That's the path. You got to think, there's a difference between the road itself and what you're doing on the road. Yeah, the road goes forever in that direction, but I'm driving that way. So if I'm driving along this road, a very steep road, by the way, but if I'm driving along this road from left to right, am I going uphill or downhill? This is the part where you speak. Uphill. All right, so I'm going uphill. And maybe here I'm flatlining a little bit, but I'm consistently going uphill. So this would be an increasing function. All right. So when looking for a section of the graph that grammar doesn't feel right. That's how I evaluate grammar, by feel, which is why I'm wrong almost all the time. When looking for a section of a graph that are no, it can't be right.
It's always so quick.
When looking for sections, plural, sections of a graph that are increasing or decreasing. Yeah, right? Sections, plural. All right, so did somebody get it already? Boom. All right, a function is increasing if, as x increases, y increases. Function is decreasing if, as x increases, y decreases. A function is constant if, as x increases, y remains constant, remains the same, RTS, remains the same. I'm actually pretty sure that that's an accepted abbreviation. I almost said definition. Abbreviation for remains the same. Like STP in science class. You know what that means? Or you're not there yet? All right, I think that might be next year. So numerically, standard temperature and pressure, in case anybody was wondering. On what interval or intervals is the function increasing? So I'm looking for where the graph is going uphill. So we're going from meow to meow, right?
Right.
Indeed. Okay. So in terms of x, because all I care about are the x values. I'm starting where? 0. I'm ending where?
Infinity.
For the increasing part?
2.
2. Are there solid points at both of those locations?
Yes.
Bracket it up. Ooh. Over bracketed. Okay. Now, the decreasing one is going to be a little bit more interesting. Oh, 2 fingers. So I'm going to have 2 intervals for where it's decreasing because it goes downhill in 2 different places. All right, the first interval is from what to what? Because again, only talking in terms of x values.
Infinity to 0.
Positive infinity?
Yeah.
Negative infinity. All right, because we're starting here. And we're ending here because we're only talking about x. All right. So infinity always gets parentheses. I'm going to move this over a smidge. The infinity, so the negative infinity always gets parentheses. The 0 is going to get brackets or a bracket because there's a solid point there. All right. Then I have the other part where it's decreasing.
Wait, there's no solid point zero.
That's not solid? I mean, my vision is shot, so
It's not negative 1.
No, it's in terms of x.
in terms only x values is what we care about.
Oh.
Yeah, that's a solid point. Okay. So the other interval for which it's decreasing, downhill. What are we looking at?
2.
Starting at 2, the x value of 2, solid point there, going to infinity. Infinity always gets parentheses. Unite the sets.
I can't draw the infinity symbol, so I can turn my paper this way and draw the
That works. 2 circles together, sideways, 8, either way, it's gonna work. I've heard arguments in both directions. Some people say they don't like doing the 2 circles because every time they do it, they miss the connector, and they end up with basically 2 zeros that are not connected to each other. Whatever works. Either that or just practice. You gotta ease into the term. That's really what it comes down to. Start at a point, go up, come down, back up, and then when you're going the other way, now this is your moment of truth. So everybody can handle that. It's a question of, am I gonna continue back in the other direction, or am I gonna start over just going in the opposite direction? It's up to you. Personally, I mean, if you kind of lean into it, then it all works out in the end. Now you have Robin's eyes from Two Titans Show. Anyway, maximum minimums. A maximum minimum, once you really think about the definition, it becomes pretty obvious. It's the highest or lowest point in the graph, but specifically it's going to be a turning point. Right? Often a turning point in the graph. It doesn't have to be a turning point in a graph, but very often it's a turning point in a graph. All right. This is where a graph changes from increasing to decreasing. All right. These points, there it is. You're going to get your typo bonus today. These points are also called extrema. All right, extrema or extremum, an extremum is a singular of extrema, right? It's another way of saying extreme values, all right? So the highest or lowest point in a graph. Most people are fine just saying highest or lowest point in a graph. Why do we have to learn this term extrema? We use it a lot in the upper levels, but also, for some reason, they seem very concerned with you knowing that for the regions. So, turning points, relative maxima or minima, right? Those are the plurals for maximum or minimum values, right? So it's just kind of getting used to the terminology. But extrema captures the idea of maxima or minima, right? So it's basically the umbrella topic that contains those other two, right? But you look at a picture, you're like, well, yeah, cool. That's definitely the highest point out of the whole graph. But then we have something called a relative maximum because it's the king of its little hill. You know, it's the highest point in its little interval here. It's not the highest overall point, but it's like the governor. You know, we got president here, we got the governor there. You know, that's really what it comes down to. It's like it's got some authority, but it doesn't have absolute authority. Right, well, the president doesn't either. But that's a different story for a different class. Anyway, if we're looking for a relative minimum, we're just looking for a point that is the lowest compared to the points that are immediately around it. So what coordinate would that be at?
0, 1.
0, -1. That would be right? Yeah. And a relative max, so a point that's higher than the points immediately surrounding it? 2, 0? Oh, 2, 3? So visually, not too bad. I mean, algebraically, it's a nightmare to come up with these things. I mean, at least at this level. End behavior. Graphs behave certain ways for extreme values of x, right? Meaning, as you get further and further away from the y-axis in terms of x. So, you know, we typically go with the -10 to 10 interval. So here it's -5 to 5, but what if I were to go out to 100 or 1,000 or 10,000? You know, what would be the behavior of the graph? Having a sense of how that graph behaves tells us a lot about the function, right? So, end behavior is basically that. That's what this verbiage is telling us. So as x approaches, whenever you see the sideways arrow, it's talking about approaching. Unless you're in a geometry class, in which case it'll mean if then, but here it means approaching. All right, is approaching. So this is telling us, basically in terms of this graph, as x is approaching positive infinity, so if I were to continue going out to the right forever, where would the y values, because again, f of x is really just talking about the y values. It's saying the y values are approaching infinity also. So never lose sight of the fact, and it's an adjustment. I didn't like it when I was a student either. This f of x nonsense, it's not nonsense. It just seems like it right now. And maybe even for this entire course. Maybe even for the next entire course. But eventually it'll stop being nonsense and it'll become second nature. and you'll understand why you're learning this notation. It'll make all the sense in the world. It just doesn't feel right now. It's like, it seems like we're purposely taking something that you understood why and making it into something less understandable just to make math hard. That's what it seems like right now. I promise you there is a reason why we're doing it. It's not to torture you, all right? So, yeah, it just, unfortunately, you have to take my word for it at this point. If you don't believe me, you don't believe me, but I'm telling you the truth, I promise. So, as x goes out to positive infinity, I think we all agree the graph's going up. It's got an arrow, which means it's never gonna stop going up. So in terms of y values, there's no reason to think it's not gonna go to infinity, right? If this pathway, if this number line goes up to positive infinity, then so will the graph itself, all right? As x goes out to negative infinity, it's weird because the arrow is pointing to the right, but it's implied that on your graph you're going to the left because it says negative infinity there. Negative infinity is this way. All right? It's like when you go into a train station and you're like, all right, I'm buying a ticket to go to Grand Central Station. And you go up to the tracks. It doesn't always say necessarily, okay, you're going to track 1, which is that way. It just says, sign, track 1. You just know, okay, well, track 1 is over there. That is the direction I'm going to go. So negative infinity is over here. Regardless of what this arrow says, negative infinity is over here in this direction. So that means I'm following the graph this way. So as I follow the graph in this direction, I'm following the curve itself. I'm going down. I'm going down forever. Down forever is symbolized as a negative infinity. So negative infinity for x in this graph corresponds to a negative infinity for y. All right? So, oh, that's the highlighter. I like to do a little table for my end behavior. Gets the job done. Some questions will call for an explanation, but how do you describe the end behavior? I mean, you could write it in words if you want, but really I care about two things. I care about x going to infinity, x going to negative infinity. All right, so if it helps, label up your graph. Put infinities wherever it makes sense to put infinities. I got an infinity here, I got a negative infinity there. You know, obviously it's not the next number after like 5 and negative 5, but you know that you're going in that direction. So if I were to follow this graph, so I'm following the curve and I'm going out in the direction, in the right-hand direction, towards positive infinity, following the graph, where am I going in terms of y?
Negative infinity.
Negative infinity. As I go to the left forever, where am I going?
Positive infinity.
Positive infinity.